Hey everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through the concept of the photoelectric effect, where we'll learn about the photoelectric effect, the meaning of the work function of a metal, Einstein's equation for a photoelectric effect, production of photoelectric current in a photocell circuit, as well as the applications of photoelectric effect. Now, this is actually a topic in the SPM syllabus of Form 5, Chapter 7, Quantum Physics. This video lesson is designed for students who are taking the SPM examination, and therefore I will only be covering the concepts which are required for students to know to answer the questions in their examinations. So do not expect a detailed discussion or explanation about the photoelectric effect in general. A little bit of a disclaimer, I am obviously not an expert in photoelectric effect. And to be honest, this concept was fairly new to me as well when this was first introduced to the new KSSM syllabus in 2021. I have done a lot of reading to prepare my lessons for my students. I have simplified the concepts in a way that makes sense to me, and hopefully it makes sense to you. I apologize in advance if there are any errors in this video. Please let me know in the comments below if any corrections need to be made. Now, in order to be able to understand this topic, you do need to have basics of the first topic of this chapter, which is the quantum theory of light. So if you have not learned that topic or do not fully understand it yet, please watch my video lesson on quantum theory of light. I have put a link to that video in the description below. And now, let's get started. So because quantum theory can be so challenging to understand, I have put in a lot of memes on these slides to try to lighten the mood. So anytime you see the meme, feel free to laugh along. So you're looking at this meme, you don't understand what's going on. There's a ray of light shining on a metal surface that pushes the electron out, which is quite simply the photoelectric effect. If you don't know what this is talking about, don't worry. By the end of this lesson, you'll understand the photoelectric effect. So before we get into the photoelectric effect, here are some famous quotes on quantum physics. So as you can see, a lot of quantum physicists do not quite understand quantum physics as well. So if you find quantum physics confusing, don't worry, you are not the only one, because even the quantum physicists themselves find it confusing. So let's get into the photoelectric effect. So the photoelectric effect happens when light shines onto a metal surface, and that light energy causes electrons to be emitted from that metal surface. How you can remember this is basically from the word photoelectric. Photo actually means light, while electric is the concept of electric charge. So the light energy is converted into electrical energy. So on this slide, we have labeled here the process of the photoelectric effect producing current, labeled in steps 1, 2, 3. The first step that occurs here is that when a light-sensitive metal surface, which is the cathode here, is illuminated with a certain light beam, electrons are emitted from the metal surface. These electrons are known as photoelectrons because they're released through the process of the photoelectric effect. Next, labeled here as number 2, the emitted photoelectrons, which are negatively charged, will leave the cathode and are attracted to the anode, which has a positive potential. Number 3, the movement of the photoelectrons from the cathode to the anode produces a current inside the circuit. The current value can be observed using the milliammeter, which shows the value of the current. Now within your syllabus, you have to learn about the LED experiment. You might or might not get to do the experiment in class, but you still have to learn the theory. So what is the aim of the LED experiment? You would conduct the experiment with LEDs to determine Planck's constant. If you can remember what you've learned about quantum theory of light, the relationship between the photon energy of light and its frequency is based on the formula E equals hf, where h is Planck's constant. LEDs, of course, refer to the light-emitting diodes. Based on your worldly experience and knowledge, you should be aware, of course, there are many different colors of LEDs. The most common one that you would see is red, but of course other colors exist. For example, green, purple, even yellow and blue. Now a lot of people think that the LED color is determined by the casing. Actually, the color of the LED depends on the metal that is used inside the LEDs. Each color of the LED has a different threshold voltage at which electrons start being produced. Planck's constant is calculated based on the gradient of the graphs obtained. So let's look into more detail about how to conduct the experiment and what this threshold voltage of each color of LED means. We will record the readings of the voltmeter and the milliammeter for the different colors of the LED. The purpose of this potentiometer is to be able to change the values of the readings on the voltmeter and the milliammeter. For those of you who have never seen a potentiometer before, put in a picture here just for you to be able to visualize it. So how you change the value of the milliammeter and voltmeter is by twisting the knob on the potentiometer. If you don't know how a potentiometer works, I will discuss that in another video. For now, we'll focus on the LED experiment. First of all, some information that you need to know about LEDs. Now, LEDs are actually the reverse of photoelectric effect. They use current to produce photons as opposed to photons producing current. Now, if you can recall what we've looked at the previous slide, the light is shown onto a light-sensitive metal and the metal produces electrons. However, in the case of the LED, electrons are supplied to the LED from the battery. That means current is flowing into the LED. The current that flows through the LED will then produce light, meaning they will produce photons. So it's the opposite of the photoelectric effect. The color of the LED is determined by the metals used inside the LED. Different metals will emit different colors. When the free electrons move into the holes of the p-n junction, photons are emitted. If you don't know what a p-n junction or what it means for the free electrons to move into the holes, I will discuss that in another video where I'll talk more about how a diode or a light emitting diode is constructed. I'm not going to discuss it in this video because it will take quite a long time. Instead, we're just going to go straight into the LED experiment. So the photoelectric effect is when light energy produces electrons, or basically light energy being converted to electrical energy. The reverse photoelectric effect in this case means the opposite. That means converting from electrical energy to light energy. So the photoelectric effect is seen normally with solar cells, where light energy from the source is taken to produce current to power the device, whereas LEDs convert the electrical energy to produce the light energy that we see. Now let's go into the concept of threshold voltage, or more accurately, the term is called activation voltage. Activation voltage, which uses the symbol VA for short, is the minimum voltage where the LED starts to emit photons. What this means is that just because you supply current to an LED does not guarantee that it will light up. For the LED to be able to emit photons, there must be a minimum voltage provided for the metal to be able to emit photons. This is a typical current voltage graph for an LED. So based on this graph, you'll find there is a particular minimum voltage that is needed before current can start to flow through the LED. Now, the activation voltage as seen on this graph over here is actually exactly the same as a junction voltage of a diode. Now, if you don't know what a junction voltage is, I'll cover that in the video where I'll explain more about diodes. For now, just recall that diodes, including LEDs, allow currents to flow in one direction only. So obviously, if you connect the terminals in the opposite direction, current cannot flow in the diode. Now, just because we connect the terminals in the correct direction does not guarantee that current can flow. Diodes and LEDs actually have quite high resistance, and a certain amount of voltage is needed to enable to force the current to flow through the diode. The minimum voltage needed to overcome this resistance and to start getting the current to flow is known as the junction voltage in a diode, or in this case, you can think of it as equal to the activation voltage. Once the activation voltage has been met, current can flow through the LED, and thereafter the photons can be emitted. Different metals which emit different colors have different activation voltages, so that's why you can see on the graph on the right hand side, the different color LEDs have different activation voltages. Now, regardless of whichever LED that is used, the shape of the graph looks like this. But different metals that produces different colors will have different values of activation voltage. So in terms of values, they will not be exactly the same, but the shape of the graphs will generally be the same. So if you were to conduct this experiment, you would normally use a range of different colors. So for example, if you do this experiment with 4 LEDs, you will get 4 graphs. So as you can see from the results, all the 4 LED colors will have a similar shape as this general graph here, which is basically a straight line starting from an activation voltage. However, obviously they don't have the same value of the activation voltage because different metals that produce different colors will have different values of the activation voltage. So how we get this graph is by getting several sets of the voltmeter and milliammeter reading, and then we extrapolate until we get the x-intercept, and this x-intercept will be the value of the activation voltage, which is, as you can see, the minimum voltage for the LED to be able to start emitting photons and for current to flow. So from the activation voltage of these 4 different graphs, we can plot a graph of VA, which is the activation voltage, against 1 over lambda, where lambda is the wavelength of the light. And the gradient of the graph can be used to find the value of h, which is Planck's constant. And the equation is m equals hc over E. Now, if you're wondering where did this equation come from, let me show you how it's derived. Now, given that we know the equation that relates the photon energy to frequency of light, where h is Planck's constant, we can substitute other equations that we know of. So for example, for the energy here, we know that photon energy can be converted to electrical energy. So I'm going to substitute the formula for electrical energy of EV into photon energy. Now, another equation which should be very familiar to you is the wave speed formula, which is V equals F lambda. But because we're going to be focusing on light energy, instead of writing V, we can write this as C equals to F lambda, where C is the speed of light. If we rewrite this equation, we would get F equals to C over lambda, where F is the frequency of the light and lambda is the wavelength of the light. We can substitute F equals C over lambda into this equation. So by substituting these two equations into E equals HF, we will get EV equals to HC over lambda. So because this is a voltage against 1 over lambda graph, let's rewrite this equation. And you'll get V equals to HC over E lambda. Comparing this equation against the graph, so because it's a V against 1 over lambda graph, you should be able to see that by comparing this against Y equals to mx, the gradient M will be HC over E. So when you conduct this experiment, you need to plot the graph of the activation voltage against 1 over lambda, calculate the gradient of the graph, and be aware that gradient equals to HC over E. And from here, to get Planck's constant, you just need to rearrange this equation. So you would get H equals ME over C, where M is the gradient of the graph, E is a charge of a single electron, which is 1.6 times 10 to the power negative 19 coulomb, and C is the speed of light, which is 3 times 10 to the power 8 meters per second. So you would use this equation to calculate Planck's constant from the results of the LED experiment. Now let's go into Einstein's photoelectric theory. So Einstein's photoelectric theory states that light is a beam of particles whose energies are related to their frequencies according to Planck's formula. When that beam is directed at a metal, the photons collide with the atoms. If a photon's frequency is sufficient to knock off an electron, the collision produces the photoelectric effect. As a particle, light carries energy proportional to the frequency of the wave. As a wave, it has a frequency determined by the particle's energy. With his photoelectric theory, Einstein won the Nobel Prize in Physics in 1921. So I'm sure you've been seeing a lot of these kind of memes throughout my slides. Again, yes, this is just to remind you that yes, a photoelectric effect is when a photon pushes an electron out, causing the electron to be emitted. So you can think of it as a photon is basically displacing or pushing the electron away. So some of the things you need to know about the photoelectric effect. For the photoelectrons to be emitted, the photoelectric effect does not depend on the light intensity. Instead, it depends on the frequency of the light that's being shown onto the metal. So this means that photoelectrons can be emitted even at low light intensities. I'll explain all this in more detail, but first we need to know what the term threshold frequency means. Threshold frequency is the minimum frequency required to produce a photoelectric effect on a metal. Now we also need to be very clear about the difference between frequency and intensity. Now the term frequency in physics means the number of complete oscillations in 1 second. So remember that when we look at the properties of light as a wave, waves have oscillations. So the frequency of light is how many oscillations there are of the wave in 1 second. The frequency of the light is related to the color of the light. Remember that according to the spectrum of light, all the different colors of light have different frequencies and different wavelengths. The photon energy is directly proportional to the frequency of light, which means that the greater the frequency of light, the greater the photon energy possessed by that light. Intensity of light, on the other hand, refers to how bright the light is. That means the greater the intensity, the greater the brightness. Intensity will affect how many electrons are released. So to show you the difference between frequency and intensity, we have two images over here. The image on the left shows us two light bulbs that have the same light color, meaning that both of them emits light of the same frequency, but you can see that they have different intensities. The bulb on the left has a lower intensity, while the bulb on the right has greater intensity. The image on the right, on the other hand, shows us four light bulbs emitting different light colors. All of them have the same intensity, meaning that all of them shine with the same brightness. But because they have different colors, this means that each of these bulbs are emitting light of different frequencies. Now another term you need to know is work function, which means the minimum energy required for a photoelectron to be emitted from a metal surface. you do need to know the equation related to the photoelectric effect. So overall, the photon energy, which is the energy carried by the light, when it shines onto a metal, there must be a minimum energy required to release a photoelectron. This is the work function as we saw on the previous slide. Remember that work function is the minimum energy required to release a photoelectron. So if the photon energy is exactly equal to the work function, that means it is just about able to release a photoelectron. If there's any excess energy, that excess energy will then be translated into the maximum kinetic energy of a photoelectron. As written here, it is a balanced energy to move the electron, meaning the kinetic energy carried by the photoelectron when it is emitted from the surface of the metal. So if you're wondering why we have the word maximum over here, it's because in this case it means that it is the highest value of the kinetic energy that the photoelectron can have. So it could potentially be lower because some energy could be lost due to friction or other sources. So to put some symbols in here to help you visualize this, basically the photon energy, which is the energy carried by light, is represented by the symbol E. And as you should recall, E equals to hf. Work function is represented by the symbol W. Now the symbol of W is derived from E equals to hf, where in this case W equals to hf naught, where f naught refers to the threshold frequency needed by the metal to be able to release that photoelectron. So F naught is the minimum frequency for that photoelectron, while W is the work or energy needed to be able to get that photoelectron to be released. So that's where this equation is derived from. Any balanced energy will then be translated into the maximum kinetic energy to move that photoelectron. And this is of course taken from the half mv squared formula. Now some of you might still be confused by, okay, what is threshold frequency, work function, and photoelectric effect? What is all this? Allow me to explain this in more detail on the next slide. So there's a lot of things going on the slide here, but I've put them all on the same slide to hopefully enable you to be able to understand it a bit better. So on the top here, we have the spectrum of visible light with the frequencies, wavelengths, and the photon energy listed out. As you should know by now, all the different shades of color have different frequencies and different wavelengths, and therefore, of course, different photon energies. By the way, this is just a credit because, of course, we've got to always credit where we get the image from. Thank you to Encyclopedia Britannica. So, let's recall, threshold frequency is the minimum frequency required to produce the photoelectric effect on a metal. You must be very clear about the difference between intensity and frequency. Intensity of light affects the number of electrons emitted, while the frequency of light determines whether or not photoelectric effect even occurs and thereafter affects the kinetic energy of the photoelectrons. This does not mean that more photoelectrons are emitted. So over here I've put a diagram where this gray color line here represents the metal and all these different colored arrows represent the light that we are shining onto this metal. As you can see from the spectrum, violet has the greatest frequency, while red has the lowest frequency. So which means that among these four colors, the blue light will have the greatest frequency among these four colors. Just because blue has a greater intensity doesn't mean that blue will release more photoelectrons compared to the other three colors. No. The property of threshold frequency is tied to the metal. Each metal has a value of the threshold frequency. So you can shine all different colors of light on it. Whatever happens to the metal depends on the metal's property, which is the threshold frequency. So let's say, for example, this particular metal has a threshold frequency of 550 terahertz. So if we look at the spectrum, you'll find that 550 Hz is about here, roughly between yellow and green. Let's look at all this colored light compared to the threshold frequency of 550 terahertz. So red light obviously is much lower than 550 Hz. Because it's less than the threshold frequency, will not be able to produce a photoelectric effect on a metal. Yellow also is less than 550 terahertz, which means that yellow light cannot produce any photoelectrons. Green light, depending of course on whether this green light has a greater frequency than 550 terahertz. If it does, yes, it can produce a photoelectric effect. This means that the photons of the green light can knock out a photoelectron. The frequency of blue light, as you can see from the spectrum, is clearly above 550 terahertz, which means that the blue light will be able to release photoelectrons as well. So if this metal has a threshold frequency of 550 terahertz, the red light and yellow light cannot produce a photoelectric effect, but the green and blue light can. Now, what's the difference between the photoelectric effect of the green and the blue light? So blue light has a greater frequency than green light, which means that the photoelectrons that are emitted by the blue light will have a greater kinetic energy because the frequency of the blue light is greater. So the green light can probably just about get the electrons to start moving, but the blue light has so much energy it can get the electrons to move a lot faster. Remember that just because blue has a greater frequency doesn't mean it'll produce more photoelectrons. No. If let's say we have the same number of photons in the green light and blue light, the same number of photoelectrons will be emitted. It's just that the blue light, due to its higher frequency, has more energy. Therefore, the photoelectrons will just move with greater kinetic energy, meaning the electrons will move faster. So remember, in order to get a photoelectric effect, it's not about the intensity of the light. So even if, let's say, we were to use red light and we use very, very strong red light, so very bright, thinking that, oh, the brighter the red light, then the higher the chances of the photoelectric effect happening, that's not true. Because the red light has a frequency that's less than the threshold frequency. The red light is not able to meet this minimum frequency for the electrons to be produced in the first place. So no matter how bright the red light is, the photoelectric effect cannot happen on this particular piece of metal. On the other hand, if you use blue light, which has a greater frequency than the threshold frequency of this metal, even if it's very, very dim, so I'm just going to make it very, very thin here to help you visualize that it's a very, very low intensity. Even if the intensity is very, very low, it is still able to produce the photoelectric effect, meaning it's able to remove a photoelectron from the surface of the metal because the frequency of the light is greater than the threshold frequency. So the photoelectric effect depends on the frequency of the light, not its intensity. Now, once that threshold frequency has been met, then when you change the intensity of light, it would be possible to get more electrons. So if you shine a brighter blue light, then yes, it is possible for more photoelectrons to be emitted because greater intensity means more photons, so more photons will cause more electrons to be emitted. So now, let's say we have different metals and we want to compare the different values that we get of the maximum kinetic energy based on the frequencies of light that we shine on those different metals. So by comparing the maximum kinetic energy against the frequency of light, we can plot the graphs for each of those metals, and by extrapolating the graphs, you'll get the x-intercept, which would be the threshold frequency, meaning the minimum frequency needed for the photoelectric effect to take place. Now, regardless of whatever metal you investigate, you'll find that for the graphs of these variables, all the graphs will have the same gradient. Taking the equation that we've learned of the photon energy equal to the work function plus the maximum kinetic energy, if we rewrite this equation to match the graph, we would get the maximum kinetic energy equals to E minus W. We substitute E equals HF in this equation, giving us maximum kinetic energy equals to HF minus W. By comparing this against the y equals to mx plus c linear law, you'll find that we have Kmax as y and F as x. Therefore, the gradient m will be h, which is Planck's constant. That means the gradient of all these graphs would be Planck's constant. The y-intercept, on the other hand, would be equal to the work function of each of these metals. So in a nutshell, the gradient of the graph would give us Planck's constant, the x-intercept will be the threshold frequency, and the y-intercept would be the magnitude of the work function. In case you're wondering why I wrote C equals W here when it's minus, it's because when you extend this, you will of course get a negative value on the y-intercept. The work function is the minimum energy for the photoelectric effect. Obviously, it cannot be a negative number. So obviously, we take the magnitude of the y-intercept, which would be the work function in this case. You cannot have work function as negative. So now that you know what a photoelectric effect is, you do need to be aware of the 4 laws of the photoelectric effect, which is basically a summary of whatever you have just learned about the photoelectric effect. Number 1, the emission of electrons does not occur for all values of frequency of light. There exists a minimum value of frequency that is needed for the emission of the photoelectrons, and this frequency is called the threshold frequency. Number 2, the number of photoelectrons emitted is directly proportional to the intensity of the incident light for a given metal and the frequency of the light. Number 3, if the frequency of incident light is greater than the threshold frequency, then the kinetic energy of the photoelectrons depends on the frequency of the light and not on the intensity of the light. Number 4, photoelectric effect is an instantaneous process. This means it occurs in no time. The time needed for an incident photon to remove an electron is 10 to the power of negative 9 seconds. So this is an example of a very simple photocell circuit. We have here the power supply connected to the milliammeter for us to be able to observe the value of the current. And in here, you have a cathode, which is basically the light-sensitive metal. And when light is shown onto this cathode, photoelectrons will be released and will then travel towards the anode, therefore completing the circuit. So this is a very basic setup of a photocell circuit. So if the photocell was built enough to be able to produce enough photoelectrons to be able to power the circuit, then yeah, you don't actually need a power supply. You can use a photocell to be able to provide power to the device. For example, your solar-powered calculators. Now, of course, different metals do have different values of work function, threshold frequency, and a maximum wavelength to produce photoelectric effect. So on this slide, we have a simple side-by-side comparison between two photosensitive metals of cesium and lithium. So cesium has a work function of 2.14 electron volts, while lithium has a work function of 2.50 electron volts. Cesium has a threshold frequency of 5.16 times 10 to the power of 14 Hz, while lithium has a threshold frequency of 6.0 times 10 to the power of 14 Hz. The maximum wavelength is of course directly related to the threshold frequency, because if you can recall about light, the greater the frequency, the lower the wavelength. So if the threshold frequency is a minimum frequency needed for the photoelectric effect, therefore, for the wavelength, it has to be a maximum value of the wavelength to produce a photoelectric current. You can actually calculate this directly using C equals F lambda, but anyway, the values are written here for you. Cesium has a maximum wavelength of 579 nanometers compared to lithium's 496 nanometers. Looking at these numbers, you can see that the relationship is the greater the work function, the greater the threshold frequency, and therefore, the shorter the maximum wavelength required for the photoelectric effect. In order to get more photoelectric current, that of course depends on the light intensity. So the brighter the light, meaning that as the light intensity increases, the photoelectric current in the photocell circuit also increases. So as you can see from these values, there is a relationship here where the higher the work function, the greater the threshold frequency, and therefore the lesser the maximum wavelength required for the photoelectric effect. Now you might also have come across this term in your textbook, stopping potential, and yes, you need to know what it means. Stopping potential is the voltage difference required to stop electrons from moving between plates and creating a current. It is essentially the minimum negative voltage required to stop the flow of photoelectrons which make the photoelectric current. Stopping potential can also be used to calculate work function. So what is a stopping potential? So to understand stopping potential, let's take a look at this diagram on the right. So this looks like our regular photocell circuit. We have our photosensitive metal here and the electrode on the other side. But this time, the photosensitive metal is not the cathode. It is the anode because it is connected to the positive terminal. That means that the electrode on this side is actually the cathode. So why is the photocell circuit set up this way? Because we want to find out what is this stopping potential. If we had the photocell circuit the normal way, where the photosensitive metal is on the cathode, you just shine a little bit of light, photoelectrons will move immediately from the cathode to the anode. In this case though, it's a bit awkward because the electrons that come out here are now moving from the anode, which is connected to the positive terminal. So if you were to shine a light onto the photosensitive metal, if the photoelectric effect can occur, that means electrons will be released from the surface of the metal. So let's say all these letter E's here represent different photoelectrons. Now, if there was zero voltage applied between the anode and cathode, the electrons can actually move over to the other electrode and complete the circuit, causing electric current to flow inside the circuit. If let's say the voltage was too low to pull the electrons back to the anode, if the electrons are able to leave with enough energy, they may be able to still move over to the cathode and complete the circuit. So basically, the stopping potential is the amount of voltage needed to be applied between the anode and cathode to stop the electrons from crossing this field in the first place. That means from leaving the metal to move across the electric field. As mentioned here, if the voltage is too low, the electrons can still leave the metal to move away. So stopping potential is the minimum voltage needed to block the electrons from moving. As the moment they come out, they go back in and the circuit cannot be completed and there'll be no electrical current in this circuit. So that's what stopping potential is. Now, I'll just repeat this one more time because I know for some of you, you'll be like, what just happened there? Don't understand a single thing that happened. Now, remember that for a typical photocell circuit, we'll just look at the image we saw in an earlier slide. A typical photocell circuit has the light-sensitive metal or the photosensitive metal on the side of the cathode. The moment the light source shines on the light-sensitive metal, electrons are released and electrons can travel easily to the anode side because this is the cathode, the negative terminal. electrons are negatively charged, which are attracted to the positive terminal or the anode, and therefore they complete the circuit very easily. So even with very, very low voltage, the electrons can travel easily from the cathode to the anode. So this circuit is kind of awkward because the photosensitive metal is now connected to the positive terminal or the anode. So the reason why we do this is just so that we can find out the value of the stopping potential. So when we shine light onto the photosensitive metal, the photoelectric effect could occur, releasing photoelectrons. If there was zero voltage between the anode and the cathode, the photoelectrons could potentially move across the field to the other electrode and complete their circuit, causing a current to flow. So if you increase the voltage a little bit, if the voltage is still too low, the electrons can still leave the metal to move away. So if you want to stop the electrons from moving, we need to apply a voltage that's high enough that prevents the electrons from moving across the field to the cathode to complete the circuit. That minimum voltage is known as the stopping potential. So hopefully this helps you understand what this is. So once you know the stopping potential, you have to be aware, of course, that the minimum electrical energy applied to the electron must be equal to the maximum kinetic energy of the electrons. So from this, you need to know the minimum electrical energy applied to the electron must be equal to the maximum kinetic energy of the electron. So what this means is that the minimum electrical energy provided by the power supply to the electron has to be equal to the maximum kinetic energy because the electron is trying to move. So this electrical energy needs to be able to counter that kinetic energy of the electrons. So that's what this sentence means. The minimum electrical energy applied to the electron must be equal to the maximum kinetic energy of the electron that's trying to move away to stop it from moving in the first place. So that's why to solve this, we use EV equals to half mv squared. So to calculate the work function is basically the minimum energy needed to have the photoelectric effect. The work function is quite simply equals to EV. So that's what stopping potential is. And now let's go into the applications of the photoelectric effect. So one of the most common uses, of course, is the usage of solar cells. For example, the LED lamps along the road, which are powered by solar cells. In daylight, the photoelectric effect of solar cells enables electrical energy to be stored in the battery. At night, the LED lamps will light up with the power from the battery. Instead of solar power, this station, or also called the Nor Power Station, is a solar power complex and auxiliary diesel fuel station located in Morocco. So at 510 megawatts, it is the world's largest concentrated solar power plant. Yes, I'm skipping the words that I don't know how to pronounce. Now, in terms of everyday usage, light detectors at the automatic doors use infrared beams and photocell switches. When the light path is disturbed, photoelectric current in a photocell circuit will be disconnected and the door will remain open. This is another application which you have definitely used in your daily life. It's an image sensor that's found in your cameras and your phones. The image sensor is the main component in high-resolution cameras. This component is used to convert light into electrical signals which can be processed to form digital images. The ISS has 16 wings of solar panels, and each wing, which measures 35 meters by 12 meters, has 33,000 solar cells. These panels are capable of generating 84 to 120 kilowatts of electricity. And that is all for this video lesson. I've only covered the theoretical parts in this topic, so if you'd like to know how to solve questions using what we've just learned about the photoelectric effect, I'll cover that in another video. In the meantime, if you found this video to be helpful, please click like and let me know in the comments below how this video has helped you. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page, that's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do check out my YouTube channel for videos on other topics which you might find helpful. Subscribe for more free physics lessons from your physics teacher, Ms. Ho. Happy studying!